Hello, we continue with section 5, and this time we are going to apply what we have learned, which is the last lesson of this section, also of the MOOC. So we are going to start with a little introduction, and then we are going to see an example that Amanda is going to propose to us. In the previous section, we studied the phenomenon of diffraction, and we saw that when the size of the hole or the obstacle was the same size as the wavelength of the propagation that we had, the phenomenon of diffraction occurred, and therefore we observed a wavefront that was typical of a point wave, which is what we have in these two holes, a circular wavefront typical of a point wave. Well, if the two holes are next to each other and the same perturbation arrives, what happens is a diffraction with 2 point waves, but there are interferences as we have seen in the previous lesson. Well, we see that the balls remain in the same place, although the perturbation is propagating. That means that it constitutes a steady state. Well, what Amanda is proposing is that we solve a problem for her. She has a wave trough, and she's built a barrier, and she's drilled 2 holes 6 centimeters apart. The waves that she has generated in the trough are 30 hertz and propagate at a speed of 15 times 10 raised to minus 2 meters per second. And she wants to determine the type of disturbance she has at a point P, which is 15 times 10 raised to minus 2 meters from one of the holes, and 12 times 10 raised to minus 2 meters from the other, and another point Q, which is 10 times 75 times 10 raised to minus 2 meters from one of the holes, and 8 times 10 raised to minus 2 from the other. Let's help her. Well, at point P we have R1 and R2, which are the distance from each of the holes to point P. As data, we know the propagation speed and the frequency of the propagation. We will determine the wavelength of this perturbation by simply dividing the velocity by the frequency. Therefore, operating, we see that the wavelength is 0.5 times 10 raised to minus 2 meters, because they were the units we had, or what is the same, 0.5 centimeters. If we see the difference in the paths that the difference between R1 and R2 travels, subtracting those distances, we see that they are 3 centimeters. We have to compare these distances with the wavelength, and this corresponds to 6 times the wavelength. Therefore, we see that since the path difference is an integer, multiple of the wavelength, the interference is constructive. This equation, this one that we have here, corresponds to a family of hyperbolas with foci at F1 and F2, where the holes are, and for each value of n, a family will be obtained. The positions occupied by these constructive interferences do not propagate. They do not change when the perturbation propagates, and therefore it is a stationary state. At point Q, which is 10, 75 times 10 raised to minus 2 meters from one of the holes, and 8 times 10 raised to minus 2 meters from the other, we operate in the same way. We have the velocity and frequency data with which we determine the wavelength, which again is 0.5 centimeters. We see the difference of paths to which it corresponds, and this time it is 2.75 centimeters. We try to express this in terms of the half wavelength, and we see that it is 11 half wavelengths. Therefore, since the difference of paths is an odd number of wavelengths, the interference is destructive, as seen in the previous lesson. Again, it is seen that the positions are fixed, and constitute a family of hyperbolas that will each be obtained by giving value to n. What have we seen this time? We have seen that when we have two holes, the phenomenon of diffraction occurs. And also, if this occurs at the same time, what happens is that there are points where constructive interference and destructive interference occur. These positions are fixed, and it doesn't depend on how the perturbation is progressing. Is that all right? Well, that's it. See you again in another MOOC. Thank you.